The main topic of the test is what, obviously? Momentum. Okay, that's what we've been looking at is momentum. So we're going to be studying, again, for this test, the idea of conservation and also the momentum impulse theory. Those are really the two things that we looked at this chapter. Obviously, we looked at the definition of momentum, and the definition of momentum being the product of mass and velocity. That was the first thing we started off the chapter with. And we went through the idea that if an object has more mass than another object, it may or may not have more momentum depending on how fast it's moving. We used examples of like football players. And on your test, you could definitely expect, remember the multiple choice I gave you where it was like which of the four have the highest kinetic energy? A, B, C, or D, and you have to figure out kinetic energy for all four of them? That's the kind of a simple problem you could expect with this formula. But this formula is not really used by itself for the most part. Usually it's in the momentum impulse theory or it's in conservation of momentum. Okay, and the conservation of momentum is the stuff we've been doing recently with collisions, inelastic and elastic. So if you're looking at this formula alone, really for this you can expect one of two types of questions. One where it's like, which of the following have the most momentum? And you could just calculate m times v for all four of them. Or a question where it might say something like this. The mass of an object doubles when the velocity triples. What is the result of that? So those problems where what factor does it increase by or what factor does it decrease by if you have a change in the momentum or in the mass or the velocity. So let's look at one of those first. So let's say that an object's mass doubles and its velocity, let's say, is quadrupled. All right, so the mass doubles and the velocity is quadrupled. What would I replace m with if I'm trying to analyze this and think about what's happening here? Instead of m, if I said the mass doubles, what would you use instead? 2m. And if the velocity quadruples, what would I use for that instead of v? 4?
Oh, 4.
Quadruple, that's right. So as a result, the only difference between these two formulas is what factor that would be really there. What's the factor that's different? If I just collect my terms, what's 2 times 4 if I move it out front? Yeah, so this is really just 8mv. So how do these two differ? Well, this has an 8, and this has a 1 in front of it, right? There's really like a 1 there. Even though there's nothing there, there's a 1 as a multiplier always. So if the mass doubles and the velocity quadruples, the momentum increases by a factor of 8. By a factor of 8. That's how you would answer a problem like this. And we did one of these, and you did one on your last test also. Some people struggled with it, where the mass and the velocity changed, and I said, what happens to the kinetic energy as a result? So this is a little bit straightforward. What if you had one where it was like this? What if the mass tripled? That's a bad color. I didn't mean to do that. The mass triples, all right? And you're told that the velocity is cut in half. Cut in half. So the mass tripling, that's easy, 3m, I already put it up. But if the velocity is cut in half, what do I write instead of v? Paul? 1/2 v. Yeah, 1/2 v, okay, cut in half. So it's literally 1/2 there. Now, when multiplying 3 times 1/2, you end up with the result of 3/2, okay, or 1.5. So what would you say about this one? You'd say it increases by a factor of 1.5 or by a factor of 3/2. What if though, God bless you. What if instead of 1/2, the velocity was cut in 4? What if the velocity was cut in 4 instead? So I change this denominator, all right? So it's cut in 4, making it 1/4. What would that give me as a result? What's 3m times 1/4 v give me if I just collect my 3/4? So how would I make a statement about this one though? How do you make a verbal statement? Because you can't say it increases by a factor of 3/4 because it's not increasing clearly. It's difficult to say, you want to say decrease. You can say decrease if this wasn't here. If the 4 was there, you could say it decreases by a factor of 4, just like that. But the 3 is there. So you can't say it decreases by 3/4 because believe it or not, that's not actually true. There's another way to say this.
Would you talk something about the percentage?
Okay, that's one thing you could say. So what percentage would it be? So you could say the momentum is 75% of what it started with. That's one way. What else?
Do you just say it's changed by a factor of 3/4?
Okay, changed, that's fine, but not increase or decrease. Very good. So if you say just it's changed by a factor of 3/4, or simply say the new momentum is 3/4 of the old momentum. Okay, but it's not increase or decrease when you have a fractional value that's between 0 to 1. It gets a little bit tricky in there. Okay, so I would be careful with my statements in those areas. All right. Now, in section 6.1, the basic idea of momentum was discussed, and then we went into momentum impulse theory. What does momentum impulse theory tell me? What do you say about momentum impulse theory, Jen?
Change in momentum is equal to force times the time.
So where's impulse in here, Jen? Because it's called momentum impulse theory, right?
Force times time.
Good. This quantity right here, this product is defined as impulse. And that's something I want to take a minute to discuss, because I feel like people didn't understand this in class based on the homeworks and the responses in your problem sets. Or not problem sets, your labs. You guys, your lab is due Friday. Good. Okay, the other class turned it in yesterday, so don't confuse that. That due date was later for you. So, impulse. Impulse is a term that's not a specific variable. So if a problem says, find the impulse felt by an object or on an object as a result of blah, blah, blah. You're not finding force, you're not finding time, you're finding the product of force and time. But the problem might not give you anything to do with force and time. So let's do an example to explain how impulse is calculated. So imagine, or write this down, an object is moving, an object of 4 kilograms, is moving with a velocity of 3 meters per second. So 4 kilograms at 3 meters every second, that's a pretty quick pace, okay? And then the object bounces off the surface. Okay, so it's moving again, 4 kilograms at 3 meters per second this way. It hits the surface and bounces off the surface, moving now at negative 5 meters per second. At negative 5 meters per second. Determine the impulse on the object. Determine the impulse on the object. Give me some givens. What are some givens you've got in this problem? What can you list already, Jake?
Mass is 4 kilograms, VI is 3 meters per second, and VF is negative 5 meters per second.
Good. Okay, notice, Jake, remember the negative because it's moving off the wall. It bounces off the wall there. So that's all we're given for a problem like this. So how can you find impulse? You don't have force, you don't have time. And impulse is defined as force times time, so it doesn't look like we can do it at first.
Well, wouldn't you find it would be, and wouldn't that be impulse because the impulse is defined?
Very good, Paul. Impulse, right here, again, I'm going to point it out. Impulse is equal to the change in momentum. That's what the momentum impulse theory actually tells me. I know we've been applying it and solving for force, or solving for the time of contact between two objects. But the real idea behind this is that the change in an object's momentum, whatever it may be, is equal to the impulse. So if you don't have force and time, and you can't find impulse by multiplying them, if you can find the change in momentum, that is the impulse. These are equal to one another. So all we need to do really is use this to find the change in momentum. What is change in momentum really? How can I rewrite that formula? What can I redefine change in momentum as?
MVF minus VI.
Okay, again, final minus initial. And what is this really? It's really PF minus PI equals FT. And good, I like that, Marcelino. You don't need to write this out. Okay, you don't need to write PF minus PI every single time. Now, let's say a problem gave you the momentum before the collision and the momentum after. If it gave you the momentum, that means you're given these two values. You're not given the mass or the velocity. Say it said the momentum is 25 kilogram meters per second before the collision. And after the collision, it's negative 12 kilogram meters per second. Those values would go in right here for PF and PI, for momentum initial and momentum finally. But in our problem, we were given mass and velocities. So as Marcelino said, let's use this bottom formula here. And again, we're not solving for force or time. We're just evaluating whatever this comes out to be right here. And that is equal to Ft. That is the impulse, really. So if you ever want to find impulse, just find the change in the object's momentum. Bless you. What do we get as an answer? It's like negative 15, right? Or no, sorry, negative 20 minus 12. Why is it a negative answer? And change in momentum will be kilogram meters per second. Why is it a negative answer? Make sense of this, please. Alessia?
If there's a change in momentum, it means that energy is lost.
No, not necessarily. That's for delta KE, Alessia. I know what you're thinking of. For delta KE comes out to be negative because energy is lost. Yeah, that's what you're thinking there.
I think as it bounces off the surface and you're losing distance because the object was initially traveling in one direction and it's traveling back.
Okay, because it changes direction. That's good. You're not losing distance, but you're changing.
Yeah, you're changing your distance.
Agreed. What other reason? There's other reasons you could answer, because that's one way you can think of it. There's another way to think. Is it the same answer you're going to give? There's one other thing. Yeah?
Yeah.
If I throw an object this way, right, and it hits the wall, which way does the wall push? So what kind of a force does the wall push with? So if the force is going to be negative, this has got to be negative, so that time is positive. So you know already, the force has got to be negative. Even though we don't know what the force is in this problem, the force applied is in the opposite direction of motion. So it's definitely a negative force. And this has to be negative, so we get a negative. Divided by this negative would give us a positive time. That's how you can do a mental check. All right? Now, that might be part A to a problem. And then in part B it says, the object is in contact with the wall for 3 seconds. Well, that's not reasonable at all. 0.3 seconds. Determine the force on the object. So what do you do? If I told you the object is in contact with the wall, Mike, for 0.3 seconds. Yeah. You don't need to redo the problem. Please don't. You already have the answer on this side, right? If you're then told that the time of contact is 0.3 seconds, put 0.3 in over here. Go ahead and divide by 0.3 to give you the force acting on the object. Okay, which will clearly be negative because this is going to be a negative. Divided by 0.3, which will give you a negative force. So you can imagine that the momentum impulse theory kind of problem will be a part A, B, C kind of problem. Okay? Or maybe just A, B, depending on what I'm in the mood for. All right. All right, let's talk about momentum impulse theory conceptually. There was a problem in your problem set that the other class asked about and had struggled with. It had to do with the gymnast. The gymnast jumps off of a balance beam and lands on a padded mat, or a mat, whatever, thick mat. Why does this, I forgot the question actually asked, but do you remember the idea?
Prevent injury. Why
Why does it prevent injury and stuff? Yeah. You want to give an explanation?
Yeah.
What's your explanation?
So the pad itself, it's padded so that it increases the amount of time that it takes for, I guess, the gymnast to come to a complete stop. And if the time is longer, then the force is less.
Yeah, look right here. That's why I agree with that. Perfect explanation. Well done. So if you're trying to figure out the amount of force on an object, it's really a function of how much time contact there is. Think about it for a second. Pick a number like 2. All right, pick 2 for time. Divide by 2. What does this come out to be? Louder. 16. I heard over here, sorry. 16, good. So divide by 2, you get 16 as your force, right? So a time period of 2 seconds is a force of 16 newtons, it would be. What if the time period was only 1 second? Divided by 1 still just. So as you get less and less time, there's more and more force. But as Paul said, as you increase the time period of contact, the force decreases. These two numbers have got to give you a product of 32. Negative, positive, I don't care right now. But they have to come up to be multiplying to 32. So if you increase the time, the force has to go down. If you decrease the time, the force has to go up. It's the exact same thing as the egg toss I mentioned to you in the very beginning of the chapter. Remember how you would never catch an egg like this? Like if Josh threw an egg at me, I would not hold my arm up and just catch it. It would go, and it would splatter. Because it hits my hand, and it's very little time period of contact. It hits it, and there's a lot of force. But if you threw something and I went like this and caught it, or caught it like this, what am I doing? I'm increasing the amount of time that I'm in contact with it for before it comes to rest. So I'm increasing the time interval at which the object is changing its momentum. Remember, change in momentum. So if you can increase that time period, what you're doing is you're decreasing the force. So that's like, and I did this yesterday, and it actually hurt me. And I don't suggest you do this, but if you want to, try to jump and land with like stiff legs.
Yeah.
Like stiff legs. It hurts. Like you feel it in your head. And I'm actually not going to do it, because yesterday in front of class I did it, and I was like, ow, like it reverberates through your body. But and then you jump, and the way you would normally land would be like with some sort of like a cushioning, right, to your legs. What you're doing is you're taking that force, that momentum, and you're using the change in momentum over a longer period of time as your knees absorb the shock. And then on the way up, you're just standing back up. But really, you're absorbing the shock on the way down, and then you come to rest, as opposed to jumping and just landing, boom, right on your feet. Like, lock your knees and just jump very lightly one time, and you'll feel it. Like, you actually can feel the force much greater.
Is this the same thing as if like a quarterback in football where they throw a short pass that's faster, the long passes are easier to catch because they're not traveling as fast?
Well, I think
the force is less?
partially, but the other part is also the fact that usually on a short pass, somebody's doing like a cross route or a quick route where the pass is coming at them and they're not moving as fast, as opposed to somebody that's a longer pass is running at the same speed as the ball. Well, the ball's catching up, obviously, but they're running at a faster speed, so it's more comparable.
Yeah.
It's also possible because, if it's a short pass, they might just quickly grab it and pull it in. Whereas a long pass, they can kind of cradle it in.
Yeah.
So that makes sense, that part, yeah. I mean, it's the same as the question, I think, did your book do a thing with a catcher? Or did I give you an example with a catcher in your lab or something at some point? There's the problem set? Yeah, like why is there padding in the catcher's glove? What it's doing, really, is it's slowing down the ball over a longer period of time. When the ball hits the catcher's glove, believe it or not, an increase in time of like even 0.1 seconds will decrease the force a lot. So by adding padding, the ball hits the catcher's glove, and it does this. It slows down, it compresses the padding, and then it stops. Instead of hitting the glove and just stopping right on impact. So, I mean, anyone, if you've ever had a catch with a regular glove, you get hit in the palm, it stings a little bit. You can actually feel it in your hand. Whereas, with the catcher's glove, it actually slows it down a lot more. They're padded, they're thicker. And it's identical to the one that Paul explained a minute ago with the gymnast. Okay? All right, so that's momentum impulse theory. That was 6-1. Now, 6 were the same mathematical type of problem and same approach. But in 6-3, we classified those interactions as elastic and inelastic. So we have to consider that when we're looking at these problems. So, first, in 6-2 and 6-3, what were the possible types of collisions, physically, not terming as in inelastic and elastic, but what can happen with collisions? What did we look at so far? Give me one example.
In an inelastic collision, the objects will stick together and then move together.
All right, so that's one option. So objects start apart, they hit together, they somehow fuse, and they move together as one. What's another possible?
They hit each other and then they bounce off.
Okay, they hit and they bounce off. Good, that's the second one. What's the third one? There's one more. We actually went over this and it's not as obvious.
One that's has much more mass than another object hits it and they both go forward.
That's a fourth. I didn't even think about that. That's totally right. You're right. So they hit and they both separate, but they both move in the same direction still. That was one in your lab, right? You saw that? Good. Yeah, that's a good point. I forgot about that. There's another one I'm thinking of too.
The one where you hit it and it stops and the other one gets the velocity.
All right, that's the fifth one. Wow, I'm not even thinking of these. Good. So they have the exact same momentum. They hit and they both stop, or this one's standing still. It hits, it stops, and it moves it over, right? So it's a complete transfer. What's the other one I'm thinking of? There's another one. How about when they start together? Remember that? Where they start together? There was an example we did with a pickup truck with a steel beam in the back. And the pickup truck was driving, and the steel beam slides out the back of the pickup truck, and as a result, the pickup truck is able to accelerate because suddenly there's much less mass in the back of it. So when two objects start together, and then they separate. So that's like an explosion. The other ones are all collisions, right? All the other ones we've talked about are collisions. But an explosion is just the opposite of a collision in our sense here, these problems. Now, With each of these problems, there are specific equations that you want to use. Depends on the scenario. On your formula sheet, if you take a look, you're welcome to look at it now. I can just tell you what they are. But on your formula sheet, I gave you 4 formulas. I told you P equals mv. I told you delta P equals ft, both of which we just discussed. And then the last 2 formulas I give you are elastic and inelastic. So if you take a look at your formula sheet so you have an idea of what you can expect, that you don't have to memorize all this stuff, you're given m1v1i plus m2v2i equals m1v1f plus m2v2f for elastic. For inelastic, you're given m1v1i plus m2v2i equals the quantity m1 plus m2 times vf. All right, now, the explosion problem is the opposite equation from the inelastic scenario. Think about it. If 2 objects start together and then they explode, right? So before the collision, remember this is our governing law always. If they start together, it means that they start like this now, as one entity. But then they explode afterward and now they're separate. So this is simply a third version that's not on your formula sheet, but it's just the opposite of the one that is on your formula sheet. The one on your formula sheet shows the lumped masses over here and these 2 separate parts over here, because that's a normal inelastic collision where they collide and stay together. Imagine this one now where they start together and then they separate afterward. Yeah?
So this wouldn't be considered an inelastic collision?
Yeah, it still is actually, yeah. It would still be considered to be inelastic. The reason being, these 2 objects in their interaction, separating it somehow, are going to use up energy to separate. They're not moving initially where they're going to hit each other. I mean, they could be moving initially. Like the truck one, the car and the beam were moving together initially. But for the most part, for these ones, it is a terrible application. But like a bomb would follow this. Like a bomb has chemical stored internal energy in it, and it's going to explode. Or like a grenade. I think I used that example, right? I said like if you play Halo or something, like grenades in the games and stuff, when they explode, what happens? Pieces of the grenade shoot off in every direction. Well, that's still conservation of momentum. It still holds true, but now you're in a ton of little pieces. That's what this is showing here. One object breaking into more than one object. Okay? What do we know about elastic as opposed to inelastic collisions? What's the major difference besides them sticking together and stuff? Besides them sticking together.
The work doesn't, there's not a negative work in an elastic collision.
Very good.
Because,
Yeah.
well, only because the mass will not, in an inelastic collision, the mass is heavier or
Okay.
greater, so the velocity is going to decrease. Whereas in an elastic collision, the mass will increase because the objects don't stick together.
The mass don't increase, but they remain the same.
Yeah.
In the elastic. That's one way of looking at it. Definitely the mass is increased and the velocity decreases, so you're going to see a difference in KEs. Good. Second?
Kinetic energy initial and kinetic energy final are equal in a elastic collision.
Why?
Because the energy just transfers to different, but there's like still the same amount of energy, nothing's lost.
Okay, correct so far, but give me more reasoning to that. So Jenny said, and this is what you were saying as well, the same kind of thing, that no work, you said there's no work done, meaning that kinetic energy is the same. That's correct, because the work kinetic energy theorem. And the idea is that you're not losing or gaining energy in an elastic collision, but why specifically? What's not happening in an elastic collision? Josh?
Is the momentum being conserved in?
Momentum is always conserved, though. It's always conserved. The question is, why is energy also conserved for elastic, and then it's not conserved for inelastic? That's really what I'm trying to get at. What's the reasoning that how they differ?
Is it because they have this 2 VIs and only 1 VI?
That affects it mathematically. I see what you're saying. That's what Jake had mentioned. The mass increases at the end and the velocity decreases. So you can see that mathematically. But physically, tell me. Physically.
For elastic, the shape doesn't deform. Well, inelastic, it kind of deforms.
Yeah, that's exactly right, Kev. So elastic collisions, they collide and separate with no deformation. Now, in a real world, there's no such thing as an elastic collision, actually. Because no matter what, anything that collides, even this marker, believe it or not, like when it hit the wall, there was a small amount of compression in the structure of this marker. So it's not an elastic collision. Why can we assume, though, that certain things are elastic? Because there's what? What's the word I use when it doesn't really affect the problem? We say it's what? It's with an N. Negligible. Close. Negatable. It's negligible. The amount of energy loss for that instance right there is completely negligible. So you can consider that to be elastic. And we give examples of pool, like playing billiards. Okay, that's a good example of elastic collision. The pool ball does not deform. It's a solid ceramic, whatever it's made of. I don't even know, what are they made of? What are pool balls made of? Some sort of, anyone know? Well, anyway, they do not deform when they contact each other. Sure, there might be a small fluctuation in it, but it's not anything major that's going to be even remotely affecting the problem. Now, inelastic, not only do they deform, but they also sometimes fuse together. Okay? In real life, most collisions are between elastic and inelastic. Okay? They're between there somewhere. So there's the two ends of the spectrum we've been talking about, perfectly elastic and perfectly inelastic. But there's a whole ton of collisions that occur in between that spectrum. So imagine two objects colliding, deforming, but then they separate. That's not elastic because they deform. It's not inelastic because they don't stick together, but it's between that. It's somewhere in between. Okay, so the majority of collisions in real life are neither elastic nor inelastic. They're somewhere in between there. Now the question becomes, when is it actually significant enough to consider the effects of where it is in between them? When can we not assume if it's elastic versus inelastic? And to answer that honestly, you need to study something like materials science more. So a topic like this would come up in an engineering course called materials science or materials engineering, where you study the interaction of molecules. You take chemistry and physics and put them together. Okay, there's a lot of math, but it's really interesting stuff. I love the course I took in this in college. But you really learn a lot more about when you can consider things negligible. When are they actually significant enough to actually consider it in the problem itself? Or when can you just drop it off for your model? Okay? So we have the idea down pat about elastic versus inelastic. All right? I'm trying to think of what else I want you to know conceptually. Were there other problem set problems that were confusing? Paul?
I think it was one, the sixth one, where there was a diver that was jumping off a diving board, and it asked when it hit the water, and it took a certain amount of time for it to he went down a certain distance, and it was asking the force of the water, that was pushing back.
Okay. My suggestion in that problem would be to, find the velocity. Do you understand the problem he's referring to right now? Does everybody know what he's referring to? The diver hits the surface of the water. As soon as he hits the surface of the water, he starts to slow down until he comes to rest at the bottom. So, you would need to know what your initial velocity is before impact, which is the velocity right before he strikes the water. It's really like VF of a free fall. Imagine a free fall, right? Zero velocity. The diver jumps off. He gets faster, impact. Right before the impact, that's your VI for the momentum problem. For this kind of a problem, for momentum impulse. Then, VF would be zero because he comes to rest at the bottom of the water. So that's your VI, your VF. You have the mass. You would have to also calculate the time that it takes for the object to stop. And then you could solve for F. Now, to find the time it takes, you were given a distance?
Yeah.
Yeah. So you would have to use the distance there involved in there to find the actual time. And I mean, if you know the distance, you can find the time if you have both your velocities also. You can find your acceleration, you can do all that work. But the key in that problem is to call the VF from the free fall, like the velocity right before it hits the water that we've calculated in chapter 1, as your VI in this problem. Because our problem for momentum starts when he hits the water, and it stops when he stops below the water. So VI is the velocity right before impact, which is the final velocity of the previous problem of projectile motion. So you're combining two topics there in one. Does that make sense?
Yeah. So would you use because it says he's jumping off. So would you use gravity?
Well, you'd have to use your kinematic equation. It depends. Were you given a height that he jumped from? You had to be given some piece of information. Was it a height? So say it was 30 meters. So you would say like, or y is negative 30 in that problem. Vi is 0. Did he fall off or did he jump off with?
Going down 30 meters.
He fell 30 meters, but did the problem say that he dove out or dove in, or did he just kind of fall off?
It says he dropped from rest.
Drop from rest. Okay. So Vi is 0. Your y is negative 30. Acceleration is negative 9.81. Solve for Vf. And that Vf in that problem is the velocity right before he hits the water. That velocity right before he hits the water is the Vi for the second problem, which is your momentum impulse problem. Okay, it's like a two-part problem for sure. That's the kind of problem you could expect on like a midterm exam, where you have kinematics and momentum in one problem. Okay, that's the kind of thing you could see. And if you work this summer, I mean, I don't know how many of you are even thinking about doing this, but some students last year that were in my physics class ended up taking pre-calculus in the summer. It was there were a few people that did this. And then you could place into calculus next year and take AP physics next year. That's the kind of problem, that's like an AP physics problem. They did a problem the other day, it was the coolest problem. It started with It started with a spring compressed, the object was released, it slid across a frictionless surface, okay, then went down a circular ramp, so it had circular motion, which is our next chapter. It hit into another object with an inelastic collision, they stuck together, which then went off a ramp as projectile motion, landing on a surface that had friction on it. So all of those ideas that we've done this year in one problem, and your goal was to figure out how far it went at the end of the problem. So you're taking all the concepts and putting them all together. That's the kind of like AP level for 12th grade if you take AP physics, that kind of question. The one from the problem set is like a little easier version of one of those. Okay, like several parts to it. Any other problems from the problem set that you had struggled on? Yeah? Sure. Sure. Great problem, okay? Because those were the tough ones, because you had to do a little bit more algebra for these, right? So let's do some... an object, let's see. Let me think real quick. Okay. Let's say that an object with a mass of 7 kilograms collides with another object with unknown mass. The object with a mass of 7 kilograms is moving at a velocity of 4 meters per second. And the unknown mass is moving with a velocity of negative 3 meters per second. So we got a 7 kilogram mass moving with a velocity of 3 meters per second. It collides with an unknown mass that's moving with a velocity of negative 3 meters per second. Did I say 3 both times there?
I think it was 4.
It was 4, yeah, sorry. So 7 kilograms moving to the right
This is an elastic.
with 4 meters per second. I have to go into that still. And an unknown mass moving left, its velocity is negative 3 meters per second. They collide, okay, they collide with one another and stick together. I'm not going to tell you the kind of collision, but you need to think about what that means. They collide and stick together, and they move together to the right with a velocity of 1.2 meters per second. So afterward, they're stuck together. So that's before, what you see up top, and this is after. Okay, and this is a mass of 7, and this is an unknown mass, M2. So right away, Jake, what do you got? What kind of collision? Good. Inelastic because they
Stick together.
Good. All right. Now, let's go ahead and try and figure out what that unknown mass is. And we know everything else. But the problem with these is that it's difficult algebraically to solve. So let's look. Before the collision, they are separate entities moving with their own velocities. So what do I write for before? Before the equal sign, what goes in here?
M1 VI1 plus M2 VI2.
Good. Okay, again, beforehand, they're moving separately, so we have the plus sign separating their momentum. Afterward, though,
VF and 1 times the quantity of them center.
yeah. And we don't need to put VF1, just VF is fine. Okay? So VF times the quantity M1 plus M2. Now, what are we trying to find? We're trying to find M2. It's up to you at this point, and I keep reiterating this. You can solve algebraically or you can solve numerically. If you're struggling with the algebraic solution here, because it is a little messy, you have to distribute VF, move your M2 over, move the M1 over here, factor out the M2. There's a lot of work algebraically. If you plug in numbers, this will be a number, this will be a number with a coefficient, or this will be a variable with a coefficient, this will be unknown, this will be a number, this will be a number. It'll make it a little bit easier on you. So you could solve this one either way. I'll solve it both ways. All right, on the right-hand side, let's plug in numbers. So we've got 7 times 4 plus M2 times negative 3 equals 7 plus M2 times 1.2. I'm just plugging in numbers in that above equation. And what we'll notice is that M2 is here and M2 is here. So it's still a messy problem to solve. Okay, let's solve it numerically. Let's continue, and then we'll go to the algebraic solution. Now, see the way I wrote that, by the way? Okay, please don't let this confuse you. M2 times negative 3 is really negative 3M2. So I'm going to write it as 28 minus 3M2. This is where I see more mistakes than anything. When you have to do some algebra and there's a negative sign somewhere that's messy, okay, just think about multiplication. It's commutative. So M2 times negative 3 is the same as negative 3 times M2. On the right-hand side, what should I do? Because I need to get M2. But M2 is on the left-hand side also. So I can't just, isolate it on one side and not the other. What do I have to do?
1.2.
Good. What's 7 times 1.2?
8.4.
8.4. That makes sense. 7 times 12 is 84. Stupid of me. Plus 1.2 M2. So far, so good? Now, how many times does M2 appear? So you have to combine like terms at this point. So what I would do personally, I would add the 3M2 over, and I would subtract the 8.4 in the same step. I would subtract 8.4 from both sides. 28 minus 8.4 is 19.6. And then I would add the 3M2. 3M2 and 1.2 M2 is 4.2 M2. Again, combine these like terms right here, and combine these like terms right here. These obviously cancel, these obviously cancel. So simply solve for M2. That's all you're doing. And then divide by 4.2. Okay? And you get 4 and change, I'm sure, right? 4.6. And our units for mass? Kilograms. All right. Numerically, great. Now let's go to algebraically. Okay, let's go to algebraically so you can see this for those of you that like to solve algebraically. And I prefer algebraically. I've mentioned it to you. Okay, but if you feel like you're going to make a mistake, I would recommend that you don't do algebraically. You do numerically. So algebraically, this would look like the following. M1 V1I plus M2 V2I equals. Now you need to distribute the VF to both. M1 VF plus M2 VF. So this kind of looks like elastic now, doesn't it? You guys see this? Doesn't this kind of look like the elastic equation? Except, here's the thing. VF is the same in both, right? When VF is the same in both of these, it means they're moving together. So you know that it's still inelastic, okay? Now, our goal is to get M2 by itself. So I would recommend taking this M2, moving it over here by subtracting the whole quantity. Take this part right here, move it over here by subtracting it. So we move this over by subtraction, and we move this over by subtraction. So the left-hand side, I start by repeating what I've got still. So this is going to be gone when I move it over. So I'm left with M2 V2I. Okay, I'm left with this right here. And now I'm subtracting this portion to the left-hand side. So minus M2 VF equals. Now this is gone because I subtracted it. I'm left with M1 VF. And I had to remember that I subtracted this over here to get rid of it. So it's minus m1 v1I. And then how do I get m2 by itself? What's the math thing you do when something is in more than one term and you want to move it out front? What is it? Yeah, factor it out. M2 is here, M2 is here. Put M2 in front. This is where your factoring skills really come in handy. How do you know what's left over? Have you been... Algebra 1 you were taught how to factor, but I know some people struggle with this. The way I teach factoring in GCF is this. Whatever you take out in front, divide it into both of what's left over here. So if you divided M2 into this, what would be left over if you just put this, and you're not going to physically do this, you're going to do this in your head. But if you divided this by M2, and divided this by M2, you're left with V2I minus VF. Alright, and then finally to get M2 by itself, divide by the quantity V2I minus VF. That gives you M2.